All right, let's just jump right in. Welcome to The Explainer. Today we're taking a completely no-nonsense, pragmatic insider's look at literally the single biggest mechanical roadblock holding back genuinely autonomous AI. Honestly, it's the million-dollar problem of our generation. We call it the Memento constraint, and it basically boils down to this massive fundamental gap between how we as humans learn and how our current frontier AI models learn. Okay, so here's our blueprint for today. We're going to cover the AI memory bottleneck, the 5 research paths, 3 structural failure modes, the lab-by-lab strategy, and finally, realistic production timelines. Let's get to it. Starting us off, Section 1, the AI memory bottleneck. So at the very heart of this bottleneck is this phenomenon known as catastrophic forgetting. Now, researchers actually identified this mechanistic problem way back in 1989, if you can believe that. Simply put, it's the super frustrating reality where training a neural network on new data aggressively degrades its performance on the tasks it already learned. It's kind of like, imagine if learning to speak French suddenly made you completely forget how to drive your car. That's essentially what's happening under the hood of our frontier models right now. And the further the new task is from the old data, well, the worse the forgetting gets. This is exactly why AI currently can't just learn on the job. To really wrap your head around why this matters so much, let's look at the contrast here. I mean, human professionals do this naturally, right? We learn continuously from our daily job experience. You do a task, you learn a little, you adopt. But frontier large language models? No way. They are trained exactly once and then they're entirely frozen at deployment. Updating them isn't just some quick little software patch you can push over the weekend. It requires full, periodic retraining cycles that take months and, get this, cost literally hundreds of millions of dollars. AI is currently stuck at this incredibly painful evolutionary bottleneck. And just look at the staggering scale of this problem. In a recent October 2025 study, researchers took a model and trained it on trivia QA facts. When they checked its performance on a previous task, natural questions, it plummeted by 89% with full fine-tuning. 89%. Even using a popular method like LoRa, the performance still dropped by 71%. But here's the really interesting part. When they used something called sparse memory fine-tuning, the drop was only 11%. That is a 3 orders of magnitude difference. It really exposes how severe catastrophic forgetting is, but it also gives us a glimmer of hope that these highly targeted new techniques might actually work. Which brings us right to Section 2, the 5 research paths. Now, the key takeaway here is that no single approach is going to fix this on its own. As we map out these 5 distinct categories, everything from in-weight learning all the way down to massive architectural shifts, you'll see that the path to actual working continual learning is going to require some pretty complex combinations. The research community is basically attacking this massive problem from every possible angle. First up, we have the direct approach, in-weight learning. This is where you modify the model's parameters directly without completely overriding the old ones. Second, researchers are literally borrowing from biology with rehearsal-based methods. This is basically just replaying past examples while the model is training on new ones. But here's the catch. Both of those methods are incredibly computationally expensive at frontier scale today. So currently, we rely heavily on the third path, which is external memory. This completely separates the memory function from the actual model parameters by using external retrieval systems. Moving on to the final 2 approaches, we have post-training mitigation. This uses techniques like RLHF and direct preference optimization. And look, they're fantastic, but they mostly act as a helpful band-aid, naturally mitigating the forgetting because the model is constantly resampling its own behavior. But true architectural fixes, those are the absolute holy grail. We're talking about designs like mixture of experts or state space models that inherently support continual learning from the ground up. They are fundamentally game-changing, even if they do require enormously expensive new pre-training runs. All right, Section 3, 3 structural failure modes. Now, fixing this isn't just a matter of checking boxes off a list. It is a deeply interdependent engineering knot. It's kind of like playing whack-a-mole. You see, catastrophic forgetting occurs during new training, right? So you try to fix that forgetting by slapping on an external memory system. But then step 2 kicks in. That mitigation creates memory pollution at scale. Your external memory gets so massive that the agent starts retrieving totally irrelevant experiences and confidently acting on them. So, obviously, you attempt to fix the pollution by tightening parameters directly. And suddenly, boom, you hit step 3, the stability-plasticity trade-off. Basically, a model that strongly resists forgetting becomes way too rigid to learn anything new, but a model that learns new things easily, it forgets way too much of the old stuff. It is a massive structural balancing act. Let's see how the big players are handling this in Section 4, the lab-by-lab strategy.
Every major lab is placing a totally different bet right now. They're treating this like a high-stakes battlefield. DeepMind, they are heavily backing a combination of external memory and post-training mitigation. Meanwhile, over at Meta, the FAIR team is really championing open-source in-weight learning methods. Then you've got Anthropic taking a pretty unique angle by pairing external memory directly with their constitutional AI framework. OpenAI, unsurprisingly, leans heavily into their incredibly strong post-training reinforcement learning infrastructure. And at the exact same time, the major Chinese labs are taking these massive swings at pure architectural approaches, pushing really hard into mixture of experts models. Everyone is just mixing and matching, desperately trying to win that capability advantage.
So when do we actually get this? Section 5, realistic production timelines. Okay, let's cut through the hype. Right now, we are sitting firmly at Tier 1. We're relying on basic external memory and RAG. By 2026 to 2027, we should hit Tier 2 with improved external self-synthesis. Then, 2027 to 2028 brings us to Tier 3, which is when sparse in-weight updates finally hit production. Tier 4 introduces actual test-time training, and that lands somewhere between 2028 and 2030. But, and this is absolutely crucial, notice that Tier 5, genuine, human-level continual learning without that catastrophic forgetting, that remains firmly in the 2030-plus horizon. It is not happening tomorrow. To really understand what this interim reality will actually feel like for us, researchers Sholto Douglas and Trenton Bricken phrased the insider consensus perfectly. They said we're going to get, quote, a broken early version of continual learning before we see something which truly learns like a human. Let that sink in. It's not going to be magic overnight. It's going to be a gradual, iterative grind of broken versions before we actually reach the Holy Grail. So the really provocative question I want to leave you with today is this. How do your 2028 strategic plans account for the structural gap between scaled-up capabilities and genuinely continual AI? Look, the raw capability is advancing incredibly fast, but genuine continual learning, it's just not arriving tomorrow. We need to stop waiting for an immediate magic fix and really start planning our operational practices around this incremental reality today. Thanks so much for joining me on this explainer, and keep learning.